Today we're going to start looking at functions that are not linear. Specifically, polynomial in general is what we're going to be taking a look at. And this is our first day. We're going to be working with different functions over the next several class periods. And we're going to start with the zero principle of multiplication. The zero principle of multiplication is what we use. So this is what we use in order to factor and solve things. So if you've had any algebra experience in your past, which all of you have, you've had this process where you tried to set things equal to zero, and you factored them to do that, and then you solved them. So the zero principle of multiplication says that if I have two values that are being multiplied, and the result is zero, then one of them had to be zero to start with. You can't multiply two things that are not zero and get zero, right? That's what this principle says. And so taking a look at problems like this is what allows us to take each of these pieces individually and set them equal to zero. So 5v plus 3 is equal to 0, and 9 minus v is equal to 0. This is unique to 0. This doesn't work if it's set equal to 5. I don't have this equal to 5 and then set each piece equal to 5 and make that work. It doesn't work like that. It only works when it's set equal to 0. So if I have it in a form where I have two pieces multiplied, which both of these examples are, okay, I'm able to set each of the individual pieces equal to 0 and solve. So at this point, it turns into the linear equations that we've been working with previously. So what would I do to solve for v and 5v plus 3? Subtract 3, which gives me 5v equals negative 3. And then what, Chase? Yeah, and then divide by 5. And I end up getting, hang on, let me shift this over. V equals negative 3 over 5. Now the other one, I need to solve for v. You actually have a couple of choices. One option is that you could add, that looks like a minus, times, it's actually minus, sorry. You could actually add the v to the other side. That would be totally fine. Or you can subtract the 9 to the other side. It doesn't make any difference. The shortest way to do it is to add the v to the other side. If I do it from this perspective, then the 9 stays put, the v moves, and the reason that's beneficial is because the v is positive when it moves. And I would be done with it from that point. So there are two answers coming out of the two individual sets of parentheses. Heat is definitely on in this building. Right? Yeah. I'm going to try and open the door and we'll see if it'll get any better movement, if we can get this hallway to stay quiet. It's definitely cooler out there. We'll try. You don't want us to open the windows, so we won't do that. All right. Next one, I actually have three pieces that are set equal to 0. However, one of them is already not able to be set equal to 0. So while technically we could put this down, it's not possible for it to happen, right? Negative 4 cannot equal 0. It just is negative 4. So it never actually helps us to do the constants. It's only the pieces that have variables that allow us to actually find any solutions. So the other two pieces that have the variable y in it will create solutions. So what is the first thing I'm going to do with, we'll call this number 1, with the y plus 3? Yeah, I subtract 3. And nicely enough on this one, that means I'm actually finished at this point because y is alone. How about on the next one? We have a couple different options. We could add the y. That's what I did on the last one, right? I added the v to both sides. I'd like to do it the opposite way on this one just so you can see it doesn't make any difference. So one option is that I can add the y, and if I add the y, I will get negative 5 equals y. The other option is that I could add the 5. So if I add the 5, I have negative y equals 5, positive, right? But in order to get the y alone, you can say you multiply, or you could say you divide by a negative 1, and y will equal negative 5. So it doesn't matter which perspective you go through. The y value in this second polynomial here, this second piece of this polynomial, is still going to be equal to negative 5. Now, both of these on the screen, if you've solved them right, right? If you made no errors in doing so, you should be able to take the solution you found and put it back in for x or v or y or whatever your variable is, and it should zero everything out. So we're going to try one just so that you can see how that works real quick. Let's just do the last one we did, y equal -5. So if we take the equation that we were given right here, and I put in -5. -5 into the first piece does not create 0, right? It's -5 plus 3, that's not 0. However, -5 into this piece will. So if I have -5, and then, was it plus, minus 5? This is that second piece right there. What is the opposite of -5? +5. Now I have a +5 and a -5, and when these add together, they give me 0, right? So I do have the ability to check all my solutions, much like I did when I was working with linear equations. Check, see if it works, plug it back in, make sure it actually equals 0. All right, so both of these were actually set up very nicely for us to begin with because they're already in factored form. So we're going to look at how we get things into factored form with the first type of factor. The first type of factor is called a common factor. So a common factor means we look at all the terms that were given and we see if they all happen to be divisible by one common quantity. That's called the greatest common factor. Maybe they're all divisible by -4. They were on number 2. That's why the -4 is in front. Okay? Maybe they're all divisible by x squared. If so, we pull an x squared out of everything. So whatever they're all divisible by is called the greatest common factor. And here's a couple of examples of how this works. So it's important to note that this is only helpful if it's in the form like I had over here where the 0 is on one side and everything else is on the other side. So if you take a look at this problem number 3, that's the form it's in. Everything on one side, 0 on the other side. So I look at each of the pieces, which is 6u squared and -12u, and I ask, what numbers and or variables are they both these pieces divisible by? So let's start with numbers. What number divides both of the numbers in the underlined portions? 3 does? 6 does too. So we're going to go with the biggest piece. That will be 6. What else divides them? Variables now. U. I've got u squared in the first one. I have u in the second one. So they're both divisible by u. Now when you factor or pull things out in front like I'm doing, what you're doing is you're doing division. Okay, that's what you're really doing. So this piece right here that said 6u squared, I am now dividing it by 6u, and I'm asking what's left over. So what is 6u squared divided by 6u? U. And you can check to make sure it works if you multiply them back together. The 6u on the outside, the u on the inside, if I multiply them together, do I get 6u squared? I do. So I've factored it out correctly. The next component is to take it out of a -12u. So -12u divided by 6u, what will I get? 2. No u's though, because the u divided out. Is it a +2 or a -2? Negative, or you could say it's subtraction, right? And again, to check and make sure that it's right, if you multiply these two together, that is the 6u on the outside, the -2 on the inside, do you get the -12u right here? Yes. So just visually checking that when you're done is a good idea, because it's really easy to leave a u into something or to leave a factor that doesn't work or has already been pulled out of something, right? To look at it and remember to pull out the variable but not the constant, something like that. So we have our pieces factored.
All we're just doing is just breaking it apart.
Mm-hmm. You're breaking them into parts by factoring, right? Once it's in this form, the problem looks just like it did over here, right? I'm going to use the zero product principle, and I'm going to set each piece equal to 0. So now I set 6u equal to 0, and I set u minus 2 equal to 0. So if 6u is equal to 0, what do I do?
Divide by 6.
Divide by 6. Not very exciting because 0 divided by 6 is 0. And again, could I check that? Sure. And I could check it into the original equation I was given. If I put 0 into 6u squared minus 12u, do I get 0? I do. It zeroes out each component. The whole thing zeroes out. The next one, I have u minus 2 equal to 0. What will I do?
Plus 2, both sides.
Mm-hmm.
Equal u equals 2.
Right. And again, I could check to make sure that it works in the original equation. That's harder to just visually check, but you could check it, right? Grab a calculator if you wish. Take 6 times 2 squared minus 12 times 2 and find out does it equal 0. And it does. I get 24 on each of the pieces. 24 minus 24 is 0. So I have my two solutions. Number 4 is not set up correctly. Why not? I don't have it equal to 0.
Yeah.
Right? Or you could say I have things on both sides. Right? There's something that's still present on both sides, like variable components, number components that are not 0. Right? So what do I need to do in order to get it to be equal to 0? Because that's where it has to start.
Break it apart.
Nope.
Find the greatest common factor.
If you multiply both sides by 0, you'll end up with just 0 equals 0. That won't help us. I mean, it would give you zeros, but it won't help.
Find the greatest common factor.
We'll find the greatest common factor, but we can't do that until they're both on the same side.
Oh. I'll subtract one side from the other.
Yeah. Okay, so it doesn't really matter which direction you go. So we'll just go to the left. Okay? So I'm going to move the piece that's on the right to the left. So now I have y squared minus 19y on the left, and I have the 0 on the right. Does that make sense?
Yep.
It's just doing the addition and subtraction pieces like we've seen done before. It's just that you're attempting to put them together instead of separate them apart, which is what we often are doing. Now, I can do the greatest common factor that Gregor was saying. So what do you see that y squared and negative 19y have in common?
Y.
Y. Plain old y this time, right? So if I take y out of y squared, what am I left with?
Y.
Y. So again, you can check. What is y times y?
Y squared.
Y squared. That's the piece at the beginning. And then what if I take a y out of the negative 19y?
19.
Negative, right?
Negative 19.
And again, you can check it by multiplying these together. Y times negative 19. Do I get negative 19y?
Yep.
I do. So I've pulled it out correctly. Once I have it in this form, I can set each of the pieces equal to 0. So the first piece is really nice because it's just y. The second piece is y minus 19, set equal to 0. So there's no more solving to do here. It's just done, right? What do I need to do with my second one?
Add 19 to both sides, and equal y equals 19.
Okay. Now, if you were to check this one into the original equation, it means that you would actually put in the 19 squared on the left, right? Sorry about that. And on the right, you would put in 19 times 19. I don't think you even have to do the multiplication to see if it's okay at this point. Is it correct? Yeah, 19 squared is exactly the same as 19 times 19, right? And the same thing for the 0. We can check those both pretty easily and pretty quickly on that one. So I have my two solutions. Any questions on those? All right. Polynomials. So I've stated that we're going to be working with polynomials in this section, but we haven't actually said what polynomials are or what they're not. So I'm going to give you some examples of things that categorize as polynomials and things that are not. So an example of a polynomial would be something like this, or at least this is one example. 1/2 x squared plus 2. This is a polynomial. Whereas x to the negative 2 is not a polynomial. Another example of polynomial would be 3x to the 4th minus 7. Another non-example would be the square root of x plus 2. We'll do one more. One more example of a polynomial would be something like 6x squared plus 2x minus 7. And an example of something that's not a polynomial is 1 over x squared plus 1. So taking a look at the examples versus the non-examples, what are some things you can tell me that the examples have in common that the non-examples somehow seem to lack?
They don't have negative exponents.
Okay, so let me rephrase what you said. Their exponents are positive. Can I say it that way? Okay, good. What do you have, Julian?
They don't have radicals.
Yeah, there's no radicals, right? And we've talked before about how radicals represent these exponents that are irrational numbers. James, Chase, I know you guys are way ahead of everybody, and that's great. We gotta no talking because it's distracting to me at least, okay? Thanks. All right, so yeah, we can't have square roots. Julian's right. What else do you notice you either can't have or you do have? Fractions. And it's not just fractions, because both of these have fractions in it.
Exponents within the fractions?
Not exponents within a fraction. You're getting closer, though. What's the difference between this fraction and this fraction?
Oh, they don't have variables.
Yeah, James is right. The variable's in the bottom,
Oh.
right? Do you notice that? Yeah, it's where the variable is located, not necessarily the numbers themselves, but the variables themselves are not on the bottom, which variables in the denominator correspond to those negative exponents that we mentioned earlier, okay? So we need positive exponents. We can have constants like the plus ones and things like that at the end, or I'm sorry, I have plus 2 and minus 7s for whatever reason. Those are the numbers. You can have the constants, that's okay, but you can't have denominators with variables in it, you can't have radicals, and you can't have negative exponents. And there's plenty of other things that we could probably say you can't have. But what we actually do have instead are expressions that look like this. And I know this looks really ugly, but the reason that it looks this way is because it's actually just an expansion that's generalized. So a common one that you're familiar with that looks a little bit easier to deal with is one like this. Does that look like a familiar form you've seen before?
Yep.
Hope so. So this would be specifically a quadratic because it's got a power 2. So there's nothing special about the power 2. It just gets its own name. We have some others that have special names too. But this one here that's written in above it allows you to go to any exponent you wish as long as those exponents are positive and they're whole numbers, right? So we have the n values here are positive, and you could say they're counting numbers. Here, we'll do that since I'm running out of space. Counting numbers. So we're looking for positive counting numbers as exponents. Oh, I already jumped the gun. There's my quadratic. It's on the next page. All right, a specific type of polynomial that you have seen before, ax squared plus bx plus c. There is one caveat that you need to make sure of. The value at the beginning has a special name. It's the coefficient like of the largest term, and it's called the leading coefficient. So whatever exponent is your biggest exponent, the number in front of that is called the leading exponent. Leading coefficient. Biggest exponent, leading coefficient. Sometimes you see things written sort of in, it's not necessarily that there's a right or a wrong order, but for example, let's say you had something like this. Leading doesn't mean that it comes in front. It actually means it only comes in front if the exponents go in descending order. So my highest degree term here is actually this one, right?
Yeah.
It's the biggest exponent. So the leading coefficient here of this polynomial is actually the value 5. Leading doesn't mean it's at the beginning. It means it's dominating, really. Power of 5 of something is dominating the value of the expression, because when you multiply something 5 times, it gets significantly bigger than if you only multiply it 3 times, which is what an exponent with the power 3 does. So oftentimes it is listed first, but it doesn't have to be for it to be called a leading coefficient. A few others: monomial, binomial, and trinomial. Monomial is a single-termed expression. What it means is there's no addition and subtraction in the problem. So a monomial would be something like x cubed, or 5x to the 4th, or 3. They're all monomials. Whereas a binomial has two of those guys added together. So it would look something like 5x cubed plus 2. There's two pieces, right? Two separate terms added together, or it could be subtracted. And if you have a trinomial, it has three pieces. So maybe you have 4x to the 9th minus 7x squared plus 2. Okay? So it's just counting the number of pieces. Mono, bi, and tri. They're the same prefixes you use in lots of other English words. Just means you have 1, 2, or 3 terms. You might ask, well, what if I have more than that? And if we have more than that in mathematics, we just call them generally polynomials. We don't have any specialized names beyond 3 terms. Okay? So we're going to take a look at solving some, at doing some factoring. I'm going to show you a method that you may or may not be familiar with, and you may or may not like it, and that's totally okay. If what I show you on the next 2 problems you absolutely hate and you don't want to ever do it again, that's fine. I'm going to show you a second method that might look more familiar to you that you're welcome to use too. But I want to give you a couple of options because what you did in the past might not be the best choice for you to do today. And you might not have liked it before and didn't know that you had a choice. There is a third option that I'm not going to teach. If you know how to use it and use it efficiently, you're welcome to use it. But we're not going to do it in class because it has limited application. So if you know a method called slide and divide and you love it, you can use it. I'm not teaching it. Okay, I'm going to teach another method that you may or may not have seen before called the AC method. And then we're going to talk about trial and error. Okay, so we're going to first talk about the AC method. The AC method takes what you know about the quadratics that were in this form, ax squared plus bx plus c, okay? So when it refers to the a and the c, these are the a and the c it's referring to. A is the number in front of x squared, c is the number that doesn't have a variable with it, okay? And so what we're going to do is we're going to identify, in each case, what the a and the c are. I will tell you, this method works for all of our polynomials, well, all of our quadratics, but it's kind of overkill for these 2 problems. So if you're looking at this and going, why would I go to all that work? The answer is because it's going to be really useful when a is not 1, and unfortunately on these problems, a is. So it's going to feel like you're doing a lot of extra work for the moment, but when we see it again and the a value is not 1, you're going to see how it's more usable, okay? So we'll encounter it again. A is 1 here, right? What's C? 10. Yeah, so A is 1, C is 10. Everybody good?
Yep.
And you keep the sign. So if the A were negative at the beginning, you'd write -1, right? You wouldn't just use the number. We're going to use the number and its sign. All right, so what I want to do is I want to take, let me do one more thing, the B value. The B value, the middle value, is simply -7, right? Let me just write it down. So we're writing all 3 of them down. All right, so A times C, when multiplied, what is A times C here? 10, yeah. So 1 times 10 is 10. And that's partly why this seems sort of silly, like it's the same thing C already was. So why did I need to do it that way? Well, if A hadn't been 1, it would change it. But here it was, okay? All right, so what we do is we take the B value and we split it into 2 pieces. The B value needs to be split into 2 pieces so that the 2 pieces I get add together to be -7, and they multiply together to be 10. Okay? So on this, it's not a very hard one to do, but I have -2 and -5. 10 doesn't have very many factors, right? It's either 10 and 1 or 2 and 5. Those are my only options. They're negative here because I need it to add to be -7, right? So I'm using -2 and -5. Okay, and then here's what we do. We are going to take this -7u in the middle, and we're going to rewrite -7u using these 2 values with u attached. -2u, -5u, and I know you're like, why did I just break it apart? I promise I'll show you. But for right now, can you at least agree with me that it's the same expression as I had before? Yeah, I just replaced it. I replaced the -7u with a -2u and a -5u, and the order doesn't matter. I did mine 2, then 5. If you had done yours 5, then 2, it'd be okay. Okay? And then what we do is we take these 2 pieces and these 2 pieces and we factor out the common factor, just like we were doing at the very beginning today. What do u squared and negative 2u have in common? U. So I take a u out. So if I take a u out of u squared, I'm left with u. And if I take a u out of negative 2u, I'm left with negative 2. We're going to do the same thing for the middle. I have negative 5u and I have positive 10.
Sorry, what?
It's okay. Negative 5u and positive 10. What do they have in common?
-5.
Yeah, either a negative or a positive 5. Let me show you what happens if I write positive 5. And then we'll change it because we really do want it to be a negative 5. If I write a positive 5, then this stays negative u and it stays positive 2. Right? Okay. The problem is my goal is that I want these two to match.
Yeah.
And right now they don't. Their signs are backwards. Agreed? So instead of pulling out a positive 5, I would rather it pull out a negative 5 because the negative 5 will change the signs. And it will also now be u minus 2. So let me run back through what happened. If I pull a negative 5 out of negative 5u, I'm left with u. If I take 10 and I divide it by negative 5, I get negative 2. That's where the negative 2 comes from.
Yep.
Okay. Now, I want you to pretend I have all this and I have all this. They're in factored piece form. What do the two circled red pieces have in common? Sorry, my color is red. It doesn't come through very well here. What does this have in common with this? U minus 2, right? Yes, u minus 2 is what they have in common. So what we do is we take the u minus 2 out in front. So when I pull the u minus 2 out from here, I'm left with u. And when I pull the u minus 2 out from here, I'm left with 5. Negative 5 specifically. And this is the factored form with the AC method. That's definitely overkill for this problem. Okay? Set each piece equal to 0 like we have on the previous slides. So u minus 2 is equal to 0. U minus 5 is equal to 0. We add our 2. U is 2. And we add our 5. And u is 5. Okay, we're going to practice that one more time. And then I'm going to show you a much quicker way to do these problems that works really nicely on these because the coefficient a is 1. It doesn't work near as nice when the coefficient's not 1, but it works great for these. Okay, so my a value is 1. What's my c?
25.
25. And my b?
10.
10. Okay, what is a times c?
25.
Still 25. So I need two numbers that multiply to 10, multiply to 25 and add to 10. So what two numbers multiply to 25? 5 and
5 plus 5.
5. And sure enough, 5 plus 5 is actually 10. Okay? The point is to get practice on an easy ones because they're going to get harder. Okay? All right, so we take our it's not u, this time it's w, right? Okay.
Yep.
Our w squared, and I change the 10w here into
5w. Well,
yeah, 5w and 5w. That's 10w, and then I have my 25. Okay, so far? So we're going to take each of the pieces. W squared plus 5w. What do they have in common?
w.
W. So if I factor out the w, what am I left with from w squared plus 5w?
W plus 5.
Mm-hmm. On the next piece, 5w and 25. What do they have in common?
5.
5. If I factor out a 5, what will I be left with?
W plus 5. Equals 0.
Yep. Okay. Everybody good?
Yep. Well, yeah.
You're good. You're doing great, Gregory. Thank you for your help today. All right. Now this piece and this piece, what do they have in common? W plus 5. On purpose. Like, we created him to do that, right? Like, that's not a surprise. It's going to happen every time if we've chosen the right values that we should have. So they're going to have a W plus 5 here. And when I take the W plus 5 out of the first piece, I'm left with W. Out of the second piece, I'm left with the 5. These are not very exciting because they match. They'll give me the same answer. But W plus 5 equals 0. I subtract my 5. And W equals negative 5. And I can do the same thing for the other one. W plus 5 equals 0. It doesn't give me anything new, but if you'd like to see it, you certainly could. There's only, sorry, that came from there. There's only one answer just because it duplicates itself. Not because there shouldn't be two. It's just there are two that match. Okay. You ready to see the other way that works so much nicer for these? But we're going to come back to AC later. Yeah, we're going to come back to AC later, but there's a purpose for the AC. It's just not a great one right now to use. But I wanted you to see it to happen first. It's trial and error. Trial and error is the only way that I learned to factor when I was in high school. Absolutely the only way. And I don't have a problem with it at all. But if you're not good at making educated guesses along the way, it sometimes can feel very frustrating. It works pretty well when your coefficient at the beginning, the leading coefficient A, is equal to 1, which it is on both of these. Okay, so it's going to work really nicely for us here, right? Here's the way trial and error would work in general. You basically jump straight to the factoring. Just jump right there, okay? The pieces at the beginning of each of our parentheses have to multiply together to give you the coefficient, or not the coefficient, but the value at the very beginning, u squared. Well, the only way u squared comes about is by multiplying u and u, right? The next thing you do is you look at your signs. The sign at the end, which is when it is positive, tells you that your two signs have to match. It means that the signs that go after the u are either both positive or both negative. Okay, that's what this is telling you. This one tells you that I have matching signs. Once I know that they're matching, I look at the term that's by b, and this one tells me what they are. If they're matching terms and the middle term is negative, then they're both negative. If they're matching terms and the middle term is positive, they're both positive. So ours are both what? Negative. And then the last thing that we do is we do much like what we did with the AC method, is that I need two numbers that multiply to 10 and add to negative 7. And specifically, you could even just say 7. 2 and 5. Whoops. And it's a good idea to make sure that it works. We know that the 2 times the negative 2 times the negative 5 is the positive 10. That's usually the easy part. Checking to make sure it equals the middle term is usually the part that causes problems, if there's problems to be had. So in the middle, the inside terms are negative 2u. The outside terms are negative 5u. When I add these together, what do we get?
7u.
What's the sign? Negative. Negative 7u. So I do have the right pieces, right? If there's a problem, this is usually where it happens. We didn't create a problem, so we're good to go. What that means is that I can now take my factored form that I had here and set each piece equal to 0. So u minus 2 equals 0. U minus 5 equals 0. I add my 2. U is 2. And I add my 5. And u is 5. It's a lot less work, right? It really is. And I promise you, this will matter. It just doesn't really show up as being very valuable yet. But we'll come back to it. Let's take a look at the second problem, much the same way. We're going to do two sets of parentheses. At the beginning of the parentheses, I need two values that multiply together to give me w squared. W and W, right? And this is why it works so nicely when the coefficient is 1. If the coefficient is 1, I don't have to worry about any number in front of W. They're just going to be 1. If the coefficient here had said 3W squared at the beginning, it actually makes things a lot more complicated.
You have to go back to the other method.
You won't have to. We'll still talk about trial and error with those. It's just harder. Yeah. All right, for these, though, trial and error works lovely. The sign at the end tells you what the signs have to do what?
Match.
They have to match. The sign in the middle tells you what the signs have to be. The signs have to be positive. So on this one, my signs are both going to be positive. And then I'm back to the same thing AC method had me do. I need two numbers that multiply to 25 and add to 10. It's 5 and 5, right? This is equal to 0, and setting each piece equal to 0 gives me W equals -5.
When we're doing our homework, do we have to show out that work of like when we get to the W plus 5, can we just like write that it equals -5?
So let me look and see what I did on the answer key. My gut tells me that obviously you can see that you don't necessarily need to show it right now, but when we don't have the variable that's quite that obvious, it will be more necessary. Let me just see what I did so that I'm answering your question in full clarity. So what I have on my answer key is that I'd like for you to set this up like this part, and then if you want to jump to there, you can. You good with that?
Simple.
Yes. And the reason is because the reason you're allowed to set them each equal to 0 is that utilizing that zero product property that we talked about at the very beginning. That's the only reason you're allowed to do it. So that's why you're showing that step that they're equal to 0 and then having the two answers. And on this one, you wouldn't necessarily need to write it out twice because they're identical. So you could definitely skip that part of it. Okay. On this next piece, we're going to reverse the process. So we're going to be given the solutions of a polynomial equation, and we're going to be asked to find an equation. So in a very real sense, we're going to start at the bottom where they're going to say, hey, u is equal to 2, u is equal to 5. What equation did that come from? Okay? So we're going to take this sort of from the bottom up in terms of the work that we've done. So here's an example, of a couple of examples of doing that. Let me make one comment too. I don't know that I've actually said this word today, roots. Roots means solutions, so just jot that down for yourself. Anytime you see the word roots, it means solutions. We see the word roots, we see the word solutions, we see the word zeros used there sometimes too. It's another equal word. Why there's so many, I don't know. I didn't make the English. I apologize. But these are our solutions. So what this is telling us, you can use whichever variable you'd like. I tend to use x's, is that x is equal to 6 and x is equal to -3. That's what this is telling us. Is that part okay? We're just identifying the pieces of what the question says to start with. It also tells us a leading coefficient here of 4. The leading coefficient of 4 just tells us we're going to start with a 4 at the beginning of our equation. That's it. So we're going to have a 4 at the beginning of whatever happens next. We're going to fill these pieces in a minute. Okay, so Simon, you know how you asked me on the last one, what work do I have to show? Okay, so on this is going to be the same kind of an answer. I need to get this to be equal to 0. I need the 6 right here, like it says x equal to 6. I need the 6 to be on the same side as x. So in a very real sense, I'm going to shift it back to the other side, much like I shifted it over to begin with when I was working on those other problems. So I'm going to do a -6 like this. So this is x minus 6 on the left, and it's 0 on the right. Is that okay? That's how it's a solution. It's a solution because when you take x minus 6, you get equal to 0. X is equal to 6. The same thing happens here if I were to shift it. Actually, I'll show it on this one. I have x plus 3 is equal to 0. So again, these two pieces are what's necessary to get to the point where I'm going. And then I take each of these pieces here and here, and they go inside the set of parentheses over here. Right, it was minus 6, sorry. X plus 3. This is the equation I'm going to be working with. But I want it in a form that looks like the questions that were given over here. Right? I want to distribute it all out. So we're going to do a little bit of algebra to distribute that on out. Hang on. That's going to be my way. All right. My advice is to do the 4 part last. Just wait with the coefficient that's in front till last. Let's just do the pieces that are in parentheses first. Do you have to do it that way? You do not, but I think it's more work if you distribute a 4 through first. Okay? So we're going to distribute first and then outer. So my first term. So what is x times x?
X squared.
X squared. What is the first term x times the last term 3?
X, or 3x.
3x. So that's the first and the outer. Then we're going to do the inner. So that's my negative 6 times my x, which gives me negative 6x. Make sure it's negative, yep. And then the last terms, I have negative 6 times 3, negative 18. All of this has a 4 in front of it, and it's set equal to 0. The pieces inside here, typically at this point something will combine, and something does. What pieces combine in the inside of our parenthesis now?
3x and negative 6x.
Right. These are considered like terms. Positive 3x, negative 6x. So what will I get if I combine those?
Negative 3x.
Mm-hmm. Okay, is that step okay? I'm about to shift it up so I can have some more space. I realize it's written on top of something. I apologize. I'll make it small when I'm done. All right, the last thing I need to do is what?
Distribute.
Distribute a 4, right?
Yeah.
So we're going to move our 4 through everything. 4 times x squared is
4x squared.
4x squared. What is 4 times negative 3x?
12x.
Negative 12x.
Negative 12x, good. And then 4 times 18? Does anybody know?
64. Wait.
You're so close, both of you. It's 72.
It is 72?
It is
That's what I
72.
said.
Is that what you said? I thought I said you said 62. It is
Did that for
72.
Minecraft, that's what we do.
That's good.
No,
It is negative 72. Yeah,
It's
and it
true.
equals 0.
I've seen it.
Okay, so this is my expression. Do you know how you could check to make sure you're right? Yeah, you could plug in the original values they gave you, 6 and negative 3, one at a time. You can't put the 6 in one place and the negative 3 in the other. You have to put them in one at a time. So like you put the 6 in for all the x's, and it should zero everything out. If you put the negative 3 in for the x's, it should zero everything out. Okay? There's absolutely no reason you can't check your solution to make sure it works. Okay, we're going to go through this one more time, and this will be our last example. This one says that we have roots of, oh, I promised you that I was going to shrink this, so at least it didn't look so funky. Put that there. This one says that I have roots of 5 and 2. What do I do first?
You get your roots.
How? What do I do?
You take 5 and 2 and you equal them to x.
Right. So I write down x equal 5 and x equal to 2. That is the first step. Then what?
Subtract from both sides to make it 0.
Mm-hmm. So this is x minus 5 equals 0.
And x minus 2 equals 0.
And whoa. All right.
Since the leading coefficient is 2, we go in the front or in the very back, like towards being parentheses.
Yeah, I would put it in the front just because it's going to show up there in a maybe a less obtrusive way. So we're going to put the 2 at the beginning. And then what's going to go over here?
Let's see, what did I? Oh.
Nobody ever here's
X
talking to
minus
me
five.
today. What am I going to do next?
X minus 5, X minus 2.
Gregory's still going to talk on your behalf. I tell ya. All right, x minus 5 and x minus 2. So we take each one of these that we have created equal to 0, and we put them in over here. Right?
Yes.
Yeah. All right, then we're going to multiply this all out. And again, I'd wait to do the 2 till last. We don't deal with it first. Let's deal with the 2 sets of parentheses first. So we will go with, oops, first and outer. So x times x is
X squared.
x squared. X times negative 2.
2x.
Mm-hmm. And then we're going to do inner and last. What are my inner terms?
Negative 5x.
And the last terms?
Plus 10.
Plus 10. Yeah. And that kind of should look familiar. We've seen this expression today, actually. What combines inside?
Negative 2x and negative 5x.
Which gives me, whoops, highlighter, which gives me
Negative 7x.
negative 7x plus my 10. And what's my last step? Distribution. So we will distribute through our 2 to everything. The first one's 2x squared. Then what?
Minus 14x.
Mm-hmm.
Plus 20. Which equals to 0.
And how can I check to make sure it's right if I wanted to?
Plug the 5 and 2 in.
Plug the 5
One
and the
at a
2 in,
time.
one at a time from here. Plug in a 5, see that it works. Plug in a 2 and see if it works. Okay?
Yep.
This lesson's a lot of work. If you want to table every discussion we had about the AC method and just use trial and error, that's probably what I would do if I were you. We'll come back to the AC method later, though.